So welcome everyone. So this is, I hope, this is a talk on multithreading, automatic compiler vectorization. So we focus on performance a lot here. I'm Ivica, I'm a performance engineer, and this is part of the things that I do. And yeah, so the talk is very practically oriented. It's not a new talk, although this is like a C++ now, and many people expect like the newest things. With performance, you want to stick like to the old and try methods. Especially there is not a lot of development in performance with the new standard C++. They focus mostly on other stuff. Okay, so the talk is structured into two parts. The first part is about multithreading, and I'll talk about OpenMP and about the OpenMP programming interface, API. And the second part is about single-threaded optimization. So how would you optimize your single-threaded application? Because when you're optimizing, many people make a very big mistake when they're optimizing multi-threaded, when they're optimizing a multi-threaded application, they're immediately jumping into multi-threading before they have the optimized single-threaded version. And you get like a speed up, but you can do much better. And we'll see how it goes. Now, are you people familiar with OpenMP? Heard of it, but have you programmed it? Yeah, okay. So a lot of this will be familiar. For people who don't know, they will learn something new. Hello. So OpenMP is a really old standard. It was introduced in 1998. So essentially like a few years after C++. The current version 6 is released in November 2024. And it has the advantages of OpenMP. It's very simple standard. The API is really simple. It doesn't make your code messy. It doesn't require you to include all kind of libraries. All major compilers support it. And for example, you can use C++ parallelization API, but it doesn't allow you to parallelize some stuff that are more complex. And OpenMP allows that kind of parallelization as well. Actually, a bit of curiosity, parts of standard library, at least what I saw, were implemented with OpenMP. Although this was a contradicting, because in code I saw the OpenMP, but then I read that they were using thread building blocks. So take this with a grain of salt. So the basics. Just a second. Okay. So the basics of OpenMP is not enabled by default, and if you want to enable it, you need to pass these compiler flags, OpenMP for GCC and Clang, or /OpenMP for Microsoft. If you don't put this flag, your code will work, but it won't be multi-threaded. It will be just single-threaded. Yeah. So with OpenMP, the whole API consists of using compiler pragmas like this one. Like this one on the right. So you see pragma-OMP. So many of the OpenMP features are exposed through compiler flag. Some of them are also exposed through functions, and you have this header called omp.h that exposes some useful functions that you need while you're parallel programming. So how does it look like? So you see here there is this printf statement. It says IAM, and then it gets OMP get thread number. So imagine you have like 4 threads, and this will print IAM 1, 2, 3, or 4. This is the idea what we want to do. When you create this pragma OMP parallel, that tells to the OpenMP runtime, create me a parallel region. Inside the parallel region, you have, example, 4 threads. While you are in the parallel region, all 4 threads are executing the same code. So this statement will be printed 4 times. At the end of the parallel region, so it ends here, there is like a join of all threads merge into one, and then the program continues as a single-threaded program. Now, if you run this program, you get output that looks like this. You see that there is a race conditions. This is not what we expect. Now the question is how will you synchronize stuff inside the parallel regions? And yeah, so, and the answer is here. So we use pragma-OMP critical. Pragma-OMP critical, you can imagine it as a mutex. So what comes after this pragma will be executed by each thread, but they will not overlap. And then you will get this output which is more reasonable, so it doesn't have these race conditions. Yes?
To what does critical apply? To the next instruction?
To the next, to the next statement, yes. But if you want like more than one, you would need to put them in brackets. Okay, so here's the look. Here is how parallel region looks like. So you have a fork at the beginning of the region, so at this place, and at the end of the region you have a join. So all the threads just become joined as one. Okay, so we have this task. So we want to use multi-threading to speed up this loop. So you see this loop on the right. It goes from 0 to n, increments by 1, and it adds a and b together. So how can we parallelize this loop with the knowledge we have until now? So any ideas? Yes?
Divide it into a bunch of however many parallel threads we have sections, and have each one handle a contiguous region.
Yeah. So if we put this parallel, if you just put the whole loop in the parallel regions, then each thread will execute the whole loop. We don't have any speed up with that. So we need to split the loop somehow. Now we can use this OMP get number of threads, so this API, and it will give us that number 4, which means we have 4 threads in that parallel region. And then we can use this OMP get num threads, which will get you the ID of the thread. So it will be either 0, 1, 2, or 3. And in this way we can split our loop at 4. Sorry?
Those are the same method.
You mean get thread now? Or something like that?
Sorry?
It's OMP get num threads and OMP get num threads.
Oh, it's an error, sorry. Sorry, it's an error. It's not OMP get num thread. It's get num threads and get thread num. I mixed them. And this is like first try at implementing this stuff. So we have a parallel region, and then we have I start and I end. And I start with, so I calculate this called chunk size. Let's say I have 1,000 iterations and I have 4 threads. So chunk size will be 1,000 divided by 4, it will be 250. So I start will be for thread 0 will be 0, and I end will be 250. I start for thread 1 will be 250 and will end at 500 and so on. Yes?
Just like, is there a thread pool, or did the Pragma OpenMP parallels just actually create threads?
So I think internally the OpenMP standard does not specify how it's done. I think that most implementation will have a thread pool, and then they won't create all the time threads, especially because you can open, then close, then open, then close. They will avoid doing that. They will have like, my guess is they would have like a few threads in a thread pool, and they'll use those if available. Okay, and this is what happened is now I manually split this loop. So each thread in the thread pool in the parallel region will execute a different part of the loop. Yes?
One other thing I'm wondering about, I also had Dennis's question, so thank you. But in this particular case here, so we have the variables declared outside of like the pragma block that we're working in here. Do these like somehow get different stacks or something? Like I'm just wondering, like, why are the threads not overwriting the start and end?
Yeah, that's the problem. This is not a good implementation.
Oh, okay, sounds good.
So this is not a good implementation because some variables in here are shared by all threads and some variables are private. And the question is which are shared and which are private. And you can answer. So since
I start and I end certainly are shared.
Are they shared?
They should be private.
They should be private.
They're private.
They are currently shared. Yeah.
You don't know. It doesn't share shared. It doesn't share private. I didn't introduce 30 topics of shared and private. Okay, I start and I end are private because each thread has its own copy and they're different between threads. What about chunk size? Is it shared or private?
It's shared.
Yeah, it's shared. So it can be shared. It can be also, I mean, you can have a local copy, but the whole thread will get the same value. What about the ABC and then?
Those are shared.
Shared, yeah. And I?
Private.
Private. Yes, that's it. Yes.
You also need to IN for the last thing. You might have an
Yeah, I know. I'll get there. Yes, Dennis?
I think that's the same problem.
Yeah, okay. So the thing is that like if you have 1,000 iterations and divide them by 4, you get like the perfect. But if you have 1,005 iterations, you need to make sure that those 5 at the end, the last thread process those as well. And here I have this. So what I did here is I marked explicitly the OpenMP offers you this shared construct, and I marked these as shared and ABC, and also as private and mark chunk size, I start and I end.
Can you just declare them inside the brace?
Yes. I'll get to that. Yeah. And there is this important thing is this default none. When you by default, OpenMP will assume that all variables are shared, I think, and this can cause problems. So you don't want to do that. Always use this default none. So this is our code. So this is a code, and this actually runs in parallel, but this is not how it's done. But it is useful to show you the difference between shared and private, and to get you the idea of how OpenMP works internally. Okay, now with regards to private variables, normally you want to avoid private variables. Just a second. You want to avoid private variables, and because if they're private, you can just declare them inside this. You can declare them inside the parallel region, and it's more readable. So you know that chunk size, I start and I end are private. So there is no private here. Dennis, you want to take something?
Yeah. So you access some variables for reading inside the section.
Yes.
But generally speaking, you may have some aliasings that would override them. Can OpenMP assume here that, let's say, C will not change?
So if you are changing C somewhere, like say you're changing in one thread C and you wrote it like this, you will have a bug. The OpenMP is not that smart; it won't do that kind of analysis. At least this is what I think.
So, shared means const?
No, shared means that all threads see the same thing. Shared are allocated, let's say, on a heap or whatever, and private are on the local threads. They are thread local variables.
So allocation. Thank you.
Okay. Yeah. So this is how you can do it, but this is not how it's done. So we want the solution that is elegant. We don't want this. This is like from this small loop we went to all this. And OpenMP is actually very good when it comes to elegant solutions. So you will see that's how it's done. Now the main problems of the previous code is the code is not that readable. So you have a lot of this boilerplate. And the second thing is the partitioning of the loop. How you split loop on the thread. It's on all the threads. It's always the same. So you know in advance which loop gets which part of the iteration space. And OpenMP has a solution for both of this. And this is how it looks like. So this is what you had earlier. And now you have something like this. You have a parallel region, and inside you have this. This is our original loop, and you see that it goes from 0 to n, and above it this is pragma-OMP4. Now pragma-OMP4 tells to the open. If we didn't have OMP4, each thread would execute whole loop. But OMP4, this is the common mistake that happens. You forget to put a pragma-OMP4. When you put the pragma-OMP4, this loop gets divided among the threads. Let's say if you have 1,000 iteration from 0 to 100 we go to thread 0, iteration from 100 to 300 we go to thread 1, and so on. So this division is done by OpenMP runtime. There is a shortened way to write this down using OMP parallel 4, so you don't have to have here two pragmas. You can just work with one, but they're essentially the same. Yes.
So it's interesting in this case here, n is still declared to be shared. When you do OMP4, is it just that OpenMP just knows it needs to inspect the loop conditions or something like that, and it just does this somehow specially? Because it looks like otherwise n would still be shared between all threads.
And it's shared between. So I don't understand the questions.
Well, basically what I'm saying is that if this is going to get broken up by different threads, it's going to have to it has to transform this loop somehow. It changes the loop termination conditions and stuff.
Yeah, it does it. The OpenMP does it automatically, and actually it's not. You don't know in advance how it will do it, and you can change it in the runtime. This scheduling of loop over threads, it's configurable with OpenMP.
Okay. But so OpenMP just understands this is a for loop and I need to change all
it knows this is a for loop, and it knows it has n iterations.
Mm-hmm.
The n doesn't change because it's constant, and it will figure things out.
Okay.
If you try to change the n inside the loop, it will complain. Okay. Yes?
Is there any benefit to declaring A, B, C, N shared as opposed to not declaring them shared? What if you declare them local? They're still constant.
But if you don't put them shared, the OpenMP will not see them. If you put the default none, they will be invisible to OpenMP.
What if you make them local instead of shared? Does it work?
But you mean you define? But how do you get the pointers ABC inside the parallel section?
how do you get other things into parallel?
You need to define, if you don't put, like, let's say you forget to put n here. What would happen? The compiler will complain it doesn't see the definition of n inside the parallel region. So you need to somehow to import your variables inside the parallel region. They can be, if you say private, they will be initialized to something, so they're there, but they're not initialized correctly. If you share, they will come from the outside. This is like interface saying, I take this from the outside. Okay? Yeah, so we covered this. Now, in order for this CppNow to work, the loop needs to be in a so-called OpenMP canonical form. So what does that mean? It has to be a for loop. So do and while loops, they don't work. Do you know why?
You can divide by n.
Yeah. Normally, when you have a while loop, normally, not always, you don't know the number of iterations. So it can, like, you have a search loop, you're looking for a 0 in a string, the end of string, and you don't know the length of the string. How can you parallelize this? How can you split this work across several? So typically, these loops are not good candidates for parallelization. And the number of iteration of the loop must be calculable in advance. That means the loop needs to be countable. So if we had a loop that goes from 0 to n, but imagine you're changing inside the loop the value of n in some way. This OpenMP would also complain that compilation would fail. The same reason. So the OpenMP runtime needs to know the number of iterations before the loop starts. It cannot parallelize other loops, yes?
Can I just use like a for each loop on a vector event?
I think the for each loops on vectors, they work. Maybe a newer standard, but does work. Then the loop must not have early exits. Like if you have a break or you have a return from you're breaking before the loop ends, it won't work also. And the loop must have only random access iterators. So you cannot parallelize loop that iterates over, let's say, a map or over a linked list. It doesn't work. Do you know why you cannot parallelize a loop over a linked list?
There's no contiguous data to split it on.
Yeah, it's very difficult to find where is the beginning. You need to know in advance where is the beginning, where is the end, and the cut places where you're cutting. And with linked lists and with maps, it's probably possible to do it, but it's not easy. Yes?
I heard somewhere that Intel compiler has early returns as an extension.
Yeah, there is an extension. I'll talk about it later. Okay, and the final thing is this loop. You see this loop? This is like a copy if loop. If a of I is greater than the value, put it in the b of j, and then increase j by 1. And this loop is also not parallelizable. Do you know why?
You don't know what to write.
The dependency from an earlier iteration, right?
Yeah.
If I start my chunk in the middle right here, and I suddenly need that if,
yes.
It came from
So the main problem is this j.
J can be used
Yeah.
from both threads.
Sorry?
The J can be accessed from both.
Yes, you need to have a copy of j which is private for each thread. But then you're copying to array and you don't know where to, you mean two threads will need to access different parts of array. You don't know where this. This can be parallelized in a different way, but just not with CppNow. Questions? Yes?
Can you modify the index variable within the loop body, or is that just reserved for the...
The I variable. No, if you do that, that makes the loop uncountable. The compiler will complain. Yes?
There are different strategies, right? You can do static or dynamic for the way it will basically... Okay, so let's say what you do in the for loop is not... It doesn't take the same amount of time depending on the index.
Yeah, there is scheduling strategies, how the OpenMP runtime divides the loop among threads. There are different, I'm not talking about it, it's a bit more advanced topic, you can investigate it, but there are different strategies and they solve different kind of problems. For example, some strategies works nice on the NUMA systems, non-uniform memory access, and some strategies work nice like on ordinary systems. They avoid some problems. Okay, the next thing is a reduction. So this loop on the right, it's called a reduction because you take like this array and then you reduce it to a single value. Now the question is, can we parallelize this? Can we parallelize this loop with OpenMP?
If you tell it that it's like the operation is fast math.
Sorry?
If you can tell it to fast math, If you can tell that you don't.
No, that's not a problem. Fast math is not a problem in OpenMP. OpenMP can produce different results for
critical section.
Yeah, you can. One of the things you can put a critical section or atomic here, but it will be like 100 times slower than a single threaded version, so it doesn't work. Okay, so the thing is how can we do that? We can parallelize this, but the question is how.
You create a local for each section and then sum your locals.
Yes, so we have a sum which is private for each thread, and then we sum them all together. So this one doesn't work. So with OMP atomic or critical, doesn't matter. And this is, so I have a parallel region here, and I have my float, which is a private per thread, and then I'm summing them all to some private, and finally I have here this PragmaMP atomic where I'm reducing all private to a big sum. Okay? Yes?
Since this is such a common operation, is there no primitive for this?
Yeah, yes, of course. This is just like to understand how it works. It's not magic. And this is how it actually does. So if you look at on the right side, so this on the left, what we have, you see this notice here, this reduction plus and then sum. This means create a private version of this sum and execute the loop. And at the end, reduce all this private sum to a public sum. Exactly the same on the left. Okay? Yeah. As far as reductions, you have these are available reductions. So plus, minus, I think this is an error. It's not there. Multiply and or this is mean, and important is mean and max. You have a mean and max reduction. And look at this code. How would you parallelize this one? If A of I is less than minimum, minimum equals A of I.
Just use the min reduction.
Yes, yes. So I have the minimum reduction here. So I have a copy private of minimum for each thread, and then I reduce them at the end to the minimum. Yes?
The logical ones, they don't short circuit, or how does it work?
Sorry?
The logical reductions, the end and the...
I don't know the details of that.
Okay.
Okay. So next are called cancellation points. Look at loop on the right. This is the loop with the early exit, because it goes through an array and looks for the value, and if it finds the value, it breaks. So what happens here? Can we parallelize this loop? Well, not with PragmaMP4. We cannot do that because the OpenMP will complain. But we can do it with cancellation point mechanism. So how do cancellation points work? So there is cancellation points work like this. You have one thread which sets a cancellation point. It says, I finished doing what I wanted to do. I found my solution result. We can all stop. It sets a cancellation point here with PragmaMP cancel 4. And then with the other threads, so the cancellations are done synchronously. So the other threads need to check whether the cancellation point is set. And they do this with PragmaMP cancellation point 4. This checks, did someone set the cancellation point? And if the cancellation point is set, and then everything stops. Yeah, so this is the mechanism that allows you to parallelize loops that have this return or break inside them. Yeah, the thing with the cancellation point, I don't know why they did it like this, but there is this environmental variable called OMP cancellation, and you need to set it to 1 or to true. If you don't do it, the cancellation mechanism doesn't work. And there is another problem with cancellation points. Sorry?
You need to set that in your local code?
No. It's with export to OMP cancellation equals 1.
Okay.
This is how you do it. I don't understand the reasoning behind it, but this is how they decided to do it. Now, the problem with cancellation point is if you check this cancellation point you check this cancellation point in each iteration of the loop, this lowers your performance because this is a check, and actually check on a variable. This is shared among all threads. Can we fix this?
You could check it every nth iteration
if
you're feeling spicy.
Yes.
Could you do this so that in a way that it would return you the first position, the found? So basically that the latest threads don't interrupt the previous threads?
Not to my knowledge. Probably you can do it. So this is like an introductory course to OpenMP, and it covers like 95% what you will ever need. But the OpenMP has a lot of things that are like a bit obscure, but you can, I guess there is a way to talk to some threads, but not to all of them.
I think his suggestion is do the loop so that none of them ever terminate early, and they all set index to the smallest value that so they're doing a min, and then you do a min reduction over all of them.
Yeah, you can do it.
Always scan all the data.
You can do it like that, but then it can happen that you have a single threaded version that works faster than the multi-threaded version. You can do that. If there is no break, that's exactly what happens. That's a min reduction, like the min index reduction. So about the thing that you're checking the cancellation point too often, you just split the loop. So instead of checking at every iteration, you're checking like every n iterations. In this case, I put about 8 iterations. Okay? Questions?
How did you pick that section size?
Normally, my experience is don't ever pick like the power of 2 because that creates problems. That can create problems. I had created several times in my life. I don't like anything that's power of 2. And yeah, you should pick a number and then play with it. There is not a good or bad one. Yeah. Yes.
What happens if multiple threads set that value before the cancellation point's checked? Like, is there some sort of way that it prioritizes one over the other?
So you see here that there is a PragmaMP critical. So if it might happen that one thread sets it, that another thread sets it, and before the cancellation. But in that case, the second thread, what the second thread wrote will be the value that's returned.
Gotcha.
Yes?
Okay.
Is there nothing like a primitive for a break?
Yeah, no, they don't have it. I think this is not like the best way to do it. It's just it's not, but yeah, we need to live with it. So I don't think this is possible to do with the standard C++ stuff, this kind of behavior. You probably have like a find, std find, which takes as a parallel in algorithms, parallel implementation, but like do that with std parallel for each. I don't think that's possible.
It has no break.
Yeah, no break. It goes from beginning to end. Okay, the next thing is a more interesting, like this is called tasks. Now look at this code here. This is like a lookup in a tree. I get and it's const correct. It's const correct. So I get this node and I get this result and I check if, so I have a tree and I go to the left part of the tree and the right subtree, and I'm finding minimum in the left part and the minimum in the right part. And this function, if you call it on a root of the tree, will get you the minimum value in the tree. Now, can we parallelize this code?
This is supposed to be recursive, right?
Yes, it is.
Okay, there's a function naming bug.
Sorry. Yeah, okay, but you get what it does. So can we parallelize it with OpenMP?
Gives the left one to the left, the right to the right.
So yeah, ideally you want to take like the left part of the tree and give it to one thread, and the right part to give it to another tree, to another thread. But the parallel, the four things we had, the four constructs we had, don't work here, right? You cannot use them. Especially these are not loops. So for this we need to use tasks. And so what a task is? Task is, you imagine it like this. I'm currently in my root. I create a task that does the left part. I create a task that does the right part. And then they call recursively the function. Then again, they create the task that does the left part and the task that does the right part. And they do recursively. And these are the tasks. So tasks are the code that tasks, but when you have a parallelism that's not immediately obvious, it develops as you process. You become more and more aware of this part can be processed independently on this one, and this part can be processed independently. These are what tasks are used for. Yes?
We could have used futures and still launch.
Yeah, but this is OpenMP. Probably, this is not like the only solution to that problem. Futures and
still launch.
Okay, I don't go into C++ in that direction. I was mostly doing this system stuff. And so how did the task work? So here you see here, I use this pragma OMP task, and then I give it the list of shared variables, and the same thing here on there. So I create a task here, and I create a task here. And finally, so I create a task for the left part of the tree, I create a task for the right part of the tree, and then I need to wait for both of them to complete. and this is the pragma-OMP task weight. When after this pragma, I can read my left value, minimum in the left part of the tree, minimum in the right part of the tree, and I can find the total minimum. But the very important thing is that you don't see any parallel region here, and actually you need another one here. You see, I have a OpenMP parallel region, and then I'm using this pragma OMP single. So I'm calling it from one thread only. When creating tasks, you need to have this driver. I call it the driver function that calls from. So otherwise, you would have like 8 parallel. Let's say you have four threads. If you don't have this pragma OMP single, that they will run four minimum. They will look for 4 minimums at the same time. Okay. Okay. Any questions? Yes.
So when the first thread will start the minimum, and then it will create tasks that will get scheduled to other threads.
Yes. This every time you see this pragma OMP task, it doesn't get run at that moment. It says to the OpenMP runtime, this code, create a task from it and run it later. Create a task from it and run it. Put it in a task queue, okay, and run it later. Okay. Yeah. So now there are some problems with this one. The main problem is that like tasks when they have very little work. Let's say just you're at the leaf nodes of the root, just one node. There is no left, no right, and you have created a task. It slows down tremendously. So when you're creating tasks, you need to be careful. You should create tasks, and at some point stop creating tasks and move on to single-threaded execution without tasks. Let's say if your total tree, so you're in one part of the tree, and under it, you know, like you have like 500 nodes. Don't create tasks anymore, because that solution will be slower than the single-threaded solution. Okay, and this is how I introduced another parameter called depth, and I was running only until the depth was 10, because I had like about 10 million nodes in a tree. And at some point, when the depth was bigger than that, I was just running the scalar version of find minimum instead of the parallel version. Okay, questions? Yeah. Okay, question for you. So we have this loop here. So it's hist of image of I plus plus. Can we parallelize this loop with OpenMP? Yes?
Well, depending how many, like image is a 255?
Yeah, it's a byte, so 1 byte.
So you have,
histogram is 256 size.
so you have a bunch of 256 size for each thread, and then you merge the
Sorry, can you repeat?
You would create a histogram for each thread, and then you merge all the histograms.
So you're saying that to create a copy of the histogram array,
yes,
then add to it, and then merge.
Yes.
Do like a reduction.
You don't need to start with a copy. You can give each one 0 histograms, and then just merge all the histograms into the parent.
Okay, yeah, that's the solution. So essentially, it's a reduction, but not on a single float. It's a reduction on an array, and this is how it's done. So, and this is like 2 or 3 times faster. It's not like super fast. Yeah, you have this reduction. You have this histogram private, which does this. Then you have this OMP4, which works on a private, and then you have this pragma OMP critical, which just reduce everything to histogram. Do you see this no weight? Do you know why I have here no weight? Can you guess? So after the for loop, there is a synchronization point. All threads need to wait. So all threads need to finish before so at this place, all the threads need to finish before you're moving on to next. But this no wait says to the OpenMP, don't wait. So as soon as this one thread is finished, it moves on to this next for loop. Okay. Okay. Any questions? Yes.
Could we parallelize the merge as well?
Sorry.
Could we parallelize the merge as well?
Yeah, but 256 is going to be cheap enough.
So
Yeah, but the question, yeah. So for 256, no. But imagine you have like 64K. Now the question: can we parallelize the merge?
Yeah, you do pairwise reductions. You two threads, you merge two threads. Two threads here, merge two threads, and merge them together.
Yeah, but I'm not aware of that you can like, so this hist priv is private to the private variable, so the other threads cannot see it, cannot access it.
You can no longer use hist priv.
So if you lift the his priv into an array of his privs,
okay,
your number of things, then you don't need a critical section when you do the reduction.
So you would need to declare the hist private outside of this, outside of the parallel regions, and you need to have like as many copies as you have threads, and then each thread can access everything. Then you can do something like that.
And someone mentioned maybe that's slower actually than doing it like this. If there's only 256 elements, how do we know what's going to be faster?
You need to try.
Try.
Yeah, like that's with OpenMP. It's always like that. You expect one thing, something else happens. A question for you: do you think it's possible? Let's say I have 4 threads and I have my loop, and I divide my loop. Is it possible to have a speedup that is bigger than 4?
Yes.
You don't answer.
Yeah.
How? Why?
Because you functionally have more L1 caches. You get 4 CPUs worth of L1 caches.
Yes. So imagine you have an array. Let's say this array doesn't fit, when you're running a single threaded and you're going over this array several times, it doesn't fit the L2 cache. It fits the L3 cache. But when you have 4 arrays and you split it into 4 parts, and each of these parts fits the L2 cache, it will be run like the speedup can be bigger than 4. Because you're getting your data from a faster part of the data cache. Yes.
So for like small stuff, there is issues with false sharing and things like that. Is there something that will be something like that for bigger chunks, like sharing pages on NUMA nodes or something like that? That will be problematic when you try to do parallelization, so that you slow down because of the caches and synchronization.
Yeah, I think it's possible. I don't know. You need to give like a specific loop so we can investigate. Right. But false sharing can happen. And yes.
To your example, I suppose it could be less than, like it could even be slower than sequential, right? Because if you have other CPUs saturating the memory bandwidth, now you have 4 CPUs competing for memory.
Yes, yeah, this happens more often than you think. Yeah. Okay, so this is like OpenMP overview. So I guess people here who haven't heard of OpenMP now have an idea how it works. There are some things we didn't mention. We did mention, but we didn't cover them, like these scheduling methods. How is a loop divided? There are several strategies how a loop is divided among several threads. Sections, similar to tasks, like you can have like one section that does one job and another section that does another job, and then they're like running in parallel, but they're independent. Then there are these single master constructs where just only one thread runs something, synchronization barriers and other stuff. So we didn't cover that. But I think you have like a good basis. If you're interested, you can investigate on your own. Now, pitfalls of parallelization, and there are many of them. Now, the parallelization is really tempting. Like what happens? You have this simple API, relatively simple, and then you just apply it on your loop and wow, you expect speed up. More often than not, the speed up is like unsatisfactory. Like you went from 0.6 to 0.5 with 4 threads, and you're like, what's going on? So this is not what I expected. And you need to be really careful with parallelization. You need to be aware of the system and what happens. The first thing is the applicability of parallelization is quite limited because because of this, when you start a parallel region, you need these threads are created and then synchronized at the end. A small loop, let's say loop with 1,000 iterations, will be typically not worth parallelizing. It just doesn't pay off. And I also told you like small task. If you have task which is like 3 nodes in a tree or something like that, it doesn't work. So you need to give the system enough work to do for it to be efficient. Okay, now a question for you. So this is a mystery performance. We have two loops, but they're drastically different speedup. So the first loop here adds A and B together. With 1 thread, it runs 0.15 seconds. With 4 threads, it runs 0.08. So the speedup is 1.87. And this on the right side, you have this square root divided blah blah, multiplied blah blah, divided again. So you have much more mathematical operation. 1 thread runs 0.25, so it's a bit slower than this one simple. And 4 threads run 0.08, which is almost the same as this very simple one. Now the input size is 128 million values. So the speed up here is 1.8, and the speed up here is 3.12. Now, what do you think happened?
The single thread for the addition was vectorized.
Both of them are vectorized.
Oh,
But the speed up is very bad speed up here.
The
Yes?
CPU's own vectorization is picking up the single-threaded one.
No.
We can hide the latency more efficiently in production.
So this was the test was run on this laptop. So it's a 5 years old like Intel setup. Yes.
I gonna get memory bandwidths.
Yes.
The left one is memory bound, and the right one is less memory bound because you do complicate that.
So, yeah. So the memory bandwidth. So this laptop has four cores, eight hyperthreads, but it has like a memory. All the data is coming from the memory because this array is really huge. And what happens with one thread, you're like not memory bound. With 4 threads, you're already memory bound. Probably with 2 threads, you're already memory bound. That means your limit, the amount of data you get from the memory, total memory bandwidth is what's limiting you, not the amount of data you can process on the CPU. So this happens for the first one. On the second one, with 1 thread, you're not memory bound. With 4 threads, you're memory bound again. Because both of these loops read the same data, A, B, and C. So here, C, A, B, and C. And with 4 threads, you're almost memory bound. And the speed up is actually more significant here because there are more work for CPU to do. So you need to pay attention with parallelization. If you have like a laptop, not like a server, which has a lot of memory bandwidth, speed ups might not be that great. With servers, it's better because servers have more memory bandwidth, so this works better. Another problem is with parallelization, you have this synchronization overhead. So every pragma-MP critical, pragma-MP atomic, end of the parallel region, end of a for loop, there is an implicit synchronization barrier, there is an implicit some kind of synchronization, and this can like kill your performance. And very often we use privatization. So we use it like several times. We create a copy of public variables as privates, and we work on those to avoid this kind of overhead. And also the problem of energy and power consumption. So energy consumption is a bit bigger. So an energy is like the power per second. Sorry, power is energy per second. So your CPU will consume more power, but not drastically more. But you know, when you have parallelization and you run it on a laptop, and instead of consuming consuming 5 watts, it consumes 20 watts with 4 threads, and you know that the sound that the laptop makes like a vacuum cleaner. This is the parallelization in place. The problem is also with the NUMA systems. So NUMA systems are systems you have more than one CPU socket, and each socket has like a local memory and a remote memory. And what happens, people who are inexperienced with NUMA systems, they allocate all the memory on one place. And this is a bottleneck. It's not like, ideally you want to have to only access local memory. And when you have multi-threading, you don't know which thread is on, which thread is locked on which thread is locked on which NUMA domain, and this can create problems. So OpenMP, you can use OpenMP in this environment. You need to be like a bit aware what's going on. And finally, bad single-threaded performance, and this is the topics of the continuation of this talk. So don't use multi-threading first. First, fix your single-threaded performance, and then you can move on to multi-threading. Because if you have a bad single-threaded performance, multi-threading will not save you. So you need to take care of that. Questions? Yes?
Did you try like TBB and other library-based approaches?
No, I didn't try TBB. Did you try TBB?
No, I don't.
Did anybody try TBB? Yes? And are you happy with it? How does it work? What kind of API is that?
You have a scheduler that they give you, so you have to understand how it works. It's not super user-friendly.
Is this better in terms of user-friendliness?
The truth is, there is no better, there's only pain.
Okay. Yes?
So say we have an application that, a program already has multiple threads, they do something with the external world, processing events, etc. Maybe there's some computationally intensive part of it, maybe on some other thread. Is it easy then to take that already existing application and take advantage of parallelism?
Yeah, if you have like a code that takes a lot of computation, does a lot of computation, then parallelization is very good for that kind of code.
But the fact that there's already other threads that are done via some other mechanism is fine.
No, but if you have other threads, then you don't need OpenMP. Like you have a fixed number of cores. OpenMP internally just POSIX. Yes?
Can you plug in your own thread pool?
I don't know. Okay, next talk. So at the end of the talk, so in the end of the next talk, we'll do like a very fun experiment. You see what's going on. So the second part of the talk is about compiler autovectorization. Now, how many people know what vectorization is? 1, 2, 3. Okay. So this will be familiar for you. So the modern CPUs can process more data in more than one piece of data in a single instruction. So instead of processing one float, they can process 4 floats. And you see here a loop on the left side, A of I equals B of I plus C of Y. On the right, you see something like this. The original loop was incrementing by 1, and the vectorized loop increments by 4, because we can process 4 floats in a single instruction. So I have here, I'm loading 4 consecutive floats from address B plus I. I'm loading 4 consecutive floats from address C plus I. Then I'm adding them 4 B's and 4 C's, and I'm adding them together to produce 4 results with this add 4. And finally, I'm storing these 4 to address A plus I. And then I increases by 4. So this is the main idea of vectorization. Now, vectorization, all CPUs support it. Servers all, desktop all, embedded, let's say, this embedded like Cortex A series supports them. Actually, I think now they're supported in some M chips, like it's called the Helium extension. And yeah, so they're very, very, very common, and it gets more and more common. So here is the example how it works. So I have here a 4711, and I'm loading it to this CPU register, and I have 3280, I'm loading it to this register, and I'm adding them together to get 4 plus 3, 7, 7 plus 2 is 9, 1 plus 8 is 9, and 1 plus 0 is 1. And then I store back all these to the memory. Now, with vectorization, you have 2 options. Let's say you have your problem, and you want to use this CPU's vector instructions. So you have options either to use the compiler autovectorization, where the compiler uses these instructions, generates for you, or to manually program this stuff using either compiler intrinsics. Compiler intrinsics are just wrappers for vector instructions in the CPU, or you can use just assembly. Now, in this talk, we are just interested in the compiler autovectorization because it's like the simple, and we can cover this in 1 hour. The manual vectorization is much more complicated process, but it allows you more stuff. Yes?
Yesterday did 2 hours with 2 talks back to back on mono stuff. Watch that on YouTube. Dennis, he wrote the STD SIMD or STD, how it's called? No, I wrote different stuff. What, say? say. I wrote Eve library. Eve library. Yeah, the Eve library, and it's like a parallel implementation, SIMD implementation of various algorithms. Is it part of the standard now? No. That's a standard SIMD different people. Aha, okay. I wasn't aware of that. I'm sorry, I arrived yesterday very late. I didn't come I wanted to come. Yeah. So how do you enable automatic vectorization? You need to pass O3 on GCC or O2 on Clang. There are some also other flags you can use, and you need to press proper architectural flags like MAVX2 if you're working on a laptop like this one. Without it, the compiler either won't do vectorization or it doesn't have the necessary instructions to do vectorization.
and the compiler will try to use this instruction to speed up computations. Now you can investigate whether a loop is vectorized or not with compiler flags. So on GCC, use this one, and this one is on Clang, and also the third one here, QVec report, is for MSVC. So all compilers actually support this in some way or another. Oh, here's the Clang's report, and this is an example of report, and you see here for this loop, which is on line 8, I don't have it, but we'll see it later. It says the cost model indicates that vectorization is not beneficial. But here on the other loop, it says remark vectorized loop, and it says vectorization with interleaved count doesn't matter. So you see here that it is the Clang is reporting this kind of stuff. The vectorization report is a bit, how I say, it's just like a compiler output debug. Compiler outputting its own debug stuff, and it doesn't look really nice, but it's helpful, so we'll go over it and you'll see. Yeah, the compiler, when you see the message, it vaguely suggests you what can be the problem, but it doesn't tell you exactly how to fix it. In this talk, we'll talk how to recognize common vectorization inhibitors, things that prevent automatic compiler vectorization, and how to fix at least some of them. Yeah, so I already mentioned vectorization inhibitors. So vectorization inhibitors in vectorization, compiler autovectorization, these are, if your data is not sequentially accessed. So imagine you have a vector, but you're not accessing, let's say, 0, 1, 2, 3, 4, 5. Instead, you're accessing 0, 5, 10, 15, or you're randomly jumping around that array. So one of the things for vectorization to be, for the compiler autovectorization to work, you need to have like sequential data access. Then if you have loop carry dependencies, we talked about that one previously. So you depend on the data from the previous iteration. For this, automatic compiler vectorization typically doesn't work. Then if you have a loop with a small trip count, so a few iterations, let's say a loop has only 3 iterations. In that case, the compiler cannot like automatically vectorize this loop because it needs at least 4 iterations or at least 8 iterations. Also loops that have many conditionals. So if you have a loop with loop and inside you have if else, and so on, these are conditionals and these don't vectorize well. They can be vectorized, but the way vectorization works, they decrease the efficiency of the vectorization. So it doesn't work very well. We will talk about this. Some of them can be fixed, some of them cannot be fixed. Let's see. So you're running your Clang report, and it reports the cost model indicates that vectorization is not beneficial. So see, Clang has a cost model, and it says like, I won't vectorize this. It doesn't work for you. So one of the reasons why the cost model might be saying that is because you're having the bad memory access pattern. Now in each program we have 4 types of memory accesses. You have so imagine you have a vector. You have a constant, one of the type is constants. Let's say you're in a loop and you're always hitting the same memory address. A0, 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 A0. So that's a constant memory access pattern. Then you have a sequential. A0, A1, A2, A3, A4, A5, and so on. So this is sequential. You have a strided. The program is hitting the memory addresses with a fixed stride. So let's say A0, A5, A10, A15, A20. So difference is always 5, but you're skipping over some element. This is called strided. And finally, you have like the worst kind of memory access, it's random. You're just going random over array. A0, A5, A3, A12, A4, and so on. Now, for efficient compiler autovectorization, most of your memory accesses should be either constant or sequential. And in order to like do this, we need to analyze, in order to fix our problems, we need to know the analysis, how to analyze the memory access pattern. So here is the loop on the right here, so it's a nested loop. So the question is, what happens when we increment the j, the inner loop by 1? So j increments by 1, we incremented by 1. So what happened to out I times n plus j? So when j increases by 1, we're just moving pointer to the next element. So this is a sequential access. For the in pointer, when j increases by 1, we are increases by n. So the stride is n. We are skipping over n elements. So this is a strided access. Index of j It's a sequential access. So when j increases by 1, we're just moving to another place. And finally, hist of index of j, this one, this is a random access because we don't know the value of the index of j, so it can jump around. It doesn't really have to, but we think it's a random access. So this is the memory access pattern analysis. You always do it from the context of the innermost loop, not from the outer loop. And you see how this iterator changes and how this pointer change. Now, when you have this, the question is, can we change this memory access pattern? And actually we can do. In this particular case, there is a loop transformation. It's called loop interchange. When we take the outer loop and the inner loop and we exchange their places. So you see here that the inner loop is now over I and the outer loop is over j. So let's do analysis again. So when the I increases by 1, this out is now a strided axis. This in now is a sequential axis. The index of j is a constant axis because it doesn't depend on I. And consecutively, the hist of index of j is also constant axis. So earlier in this place, we had like a random, 2 sequential, and 1 strided. And now we have 2 constant, 1 strided, and 1 sequential. And this loop, the second loop, has a better memory access pattern. Yes?
This is assuming I and j are both very large. Is that correct?
Well, they're reasonable, not very large, like 1,000, it's also fine.
Okay.
So it's a matrix, 1,000 by 1,000, it's a huge matrix. It's 1 million elements. So yeah, this is the memory access pattern analysis. Now can you do it? So this is on the left. So this is a matrix multiplication, 3 nested loops. And here we have the C of I of j equals C of I of j plus A of I of k times B of k of j. And then I do this loop interchange. Let's do the analysis. So the C of I of j, so the innermost loop is over k. What is the memory access pattern of C of I of j?
Constant.
Constant, okay. And A of I k?
Sequential.
Yes, and this one?
Strided.
Strided, yes. And let's do this. So we had a constant, sequential, and strided. And this one?
Constant.
No, the inner loop is over j.
Yeah.
Sequential. This one is here is?
Constant.
And this one?
Also sequential.
Yes. So we have 2 sequential here and 1 constant. And here we had 1 constant, 1 sequential, 1 strided. So this loop is actually better as far as memory performance is concerned. And actually with the compiler autovectorization, you have the load and store instruction. The most efficient one just work with consecutive. So they work with sequential. With strided, it's possible to do vectorization, but it's more complicated. And the compiler can automatically vectorize this loop, but this one it will complain about the cost analysis. Yes?
If the variables aren't volatile, could the compiler optimize by performing the loop interchange?
Compilers in principle can do that, but they never do it. The only ones I saw it was some kind of scientific compiler for some kind of scientific which did it. But then when we added the pragma OMP, it reverted it. And then we had like the parallel version which was slower than the single threaded. And it was like, what's going on here? Doesn't make any sense. Yes?
Might that be due to aliasing, like between input and output? Like the reason compilers don't automatically do it is
yeah, we get to that. We'll get to that. Yeah. And if you have like a large enough matrix, this code can be like 3 or 4 times or even 10 times faster than the one on the left. And this is like just a starting point. So you can use other things to other techniques to speed up further with memory optimizations like loop tiling, but just too much, I cannot cover it here. Okay, so this was loop interchange when you have perfectly nested loop. When the inner and the outer loop, there are nothing in between, no statement between them. Now the question is, can you do loop interchange on this loop? You have this sum and this auto W, which prevents, like, you cannot just flip them. You cannot exchange the outer and the inner, it won't work. So how can you do this? Yes?
Can you add image to the output directly?
Well, you can. I mean, you can.
That's division, sorry.
Yeah, there is division, but you can. Like, instead of this Sum you can have out of W, initialize to null, then you do this summing, and at the end you divide out of W by height, and that's it. You can do that, but that's not enough. If you need to do what?
You keep an array of sums.
Yeah, that's the same. So you're proposing an array of sums, and he just used out of W instead of sum.
Sure.
It's the same thing. So you need to move these statements to some other loops, the first one and the last one. And this is how it goes. So I did the same thing as Dennis proposed. Instead of sum, I have out of W. And I initialize it in the first loop. And then here I do loop interchange. And finally, I do this thing with the division. Now look at here. Let's have, what's the access pattern for image in this one? Strided. And this one?
Sequential.
Yeah. So this one vectorizes and this one doesn't. Yeah. Any questions?
What's the realized performance gain here?
Normally with the memory access, fixing memory access pattern has the biggest performance, and it can be going from 2 times, 3 times, 5 times, 10 times. I saw 10 times faster, especially if you have big data structures. For smaller, it doesn't matter that much, but for bigger, it does. Yeah, and also if no vectorization happens, it's still better. The memory subsystem became so much, I had a new laptop at work and I tested some of these examples and there was no difference whether you're doing addition or division. And addition is 1 cycle and division is 25. Just because the memory, when you're getting data from the memory, this is how it's slow. Okay, questions? Okay. The next thing is non-sequential memory accesses. So I have this struct. It's about classes, and in open object-oriented programming is full of classes. So you have this structure, float x, y, z, and then I have this another structure called bar, which has 2 instances of foo. And what is the layout of my bar array, which is 1024 instances of bar t? How is it stored in memory?
It's pairs of triples.
Yes, pairs of triples. So 40x, 40y, 40z, 40x, 40y, 40z, 41x, 41y, 41z. Okay? And this is not a good thing for vectorization, for compiler automatic vectorization. So Dennis can testify.
Not good.
Not good, yeah. It's not my fancy, right? So this layer is called array of structures. And the array structure is very common in object-oriented programming. It is difficult to vectorize. In this particular case, it was probably it could be done, but in general, no. Because you have, let's say I want to do this kind of processing on X and different type of processing on Y and another type of processing of Z. And let's say I want to do addition on X and multiplication on Y and division on Z. So it's not possible to, I don't have an instruction that does on one, so you have 4 values in a register and does plus on 1 value and multiply on 2nd and divide on 3rd value of the register. That doesn't exist. So the solution for this is to change the memory layout to struct of arrays. So this is how it works. So originally I had this foo xyz, and now I have foo so a struct of arrays, which is a pointer to x. So all x's are stored in one array, and all y's are stored in another array, and all z's are stored in another array, and so on. And this with vectorization helps a lot because you get you get 4 x's, and you get 4 y's, and you get 4 z, and you do the same kind of operation on all of them. Yeah, this makes vectorization quite trivial. Questions? Yes?
So both in Eve and a few other implementations have some things that would generate SOA layout for you from tuple. So if you can write code and pretend that it's still the old code you know, and it will do this thing.
They have a code that automatically converts array of structure.
Yes, you code that takes a tuple, so not a struct, but a tuple.
Okay, that's the same thing.
No, you have good names for structure.
But can I just cast in the ugly way? Cast that the tuple has the same memory.
You can do something.
Yes.
Like that. Yes.
Okay. Well, that would work. Yes.
For reflection will also enable libraries to do this with metaprogramming.
When? I mean, it will be alive until when that happens. Yes?
Just a comment that this kind of reminds me of Mike Acton's talk on data-oriented programming.
Okay. We had like I was working with one customer, and then we had to do this complete change. They had these nested structures, and it was like terrible for vectorization, and we had to undo them completely. And this kind of transformation is not trivial, because it's just, you need to change a lot of code for it to work. Like the loop interchange, you just change one loop, but this one is more complicated. Okay, the next vectorization, next message you see, it says the cost model indicates that vectorization is not beneficial. Again, the cost model, same as previously, but doesn't tell you what's wrong. And this happens when you have too many conditionals. So conditionals are like problems for vectorization. So the problem is that if you have if and then else, what's in the if part of if body and the else body, both of them have to get evaluated. Okay, and this creates a problem because you're running the same code, you're running two codes, you're running the instruction two times, and then there is an instruction that picks between the if or the else. This is how the vectorization works, and we want to avoid this. If you manage to get rid of condition or decrease the number of conditions, generally this increases the quality of vectorization. Okay, I divided conditions depending on the type of conditions, and the first one are called loop invariant conditions. So look at this loop here. It has A and B and N, and inside the loop I have if B, then B of I plus equal 1. But what's the problem here? This value of B doesn't change while the loop is running. It is either null or it is not null. So how can we fix this?
Two loops.
Two loops, yes. One loop when B is true and the other loop when B is false. And actually this is quite common optimization, and compilers will do it. It's called loop unswitching, and compiler just creates two copies of the same parameter, same loop, one when the condition is true and the other when the condition is false. But this transformation leads to code explosions. Imagine you have like 4 parameters. You need to have 2 to the power of 4, 16 versions of the loop. And at some point, compiler just says that this code is too big, don't do it. So this optimization will not be enabled if you're compiling with OS, so optimized for size. Yes?
Would branch prediction not make it so that that's almost as fast as the other one?
No, you have one instruction that is entering the pipeline, it's being processed. It is fast instruction, but it's still an instruction. Yeah? Yes?
And no vectorization.
Yeah, especially it can prevent vectorization. It's not that even, it can prevent, completely stops. There is no vectorization. Compiler says, cost says, and so on. Yes?
Just to say, I don't know about compilers that do it. I have to do it manually all the time.
So they must do what?
I have never seen this done automatically. I have to do it manually all of the time.
I saw it done automatically because when I did it manually, it didn't change the performance. So some compilers do it. Like Clang it's famous for loop unrolling. Every time I see ASM,
I'm using Clang.
Okay.
We could probably throw that example into Godbowl, and if that example doesn't do it in Godbowl, we're doomed.
Yeah. Okay, the second type of loop invariant conditions is called iterator dependent. And there, if you see here, this condition here, it depends only on the iterator I and j. It doesn't depend on the data. What this means is that this condition is predictable. You know when it will be true and when it will be false. And then you can evaluate it before this loop starts. So how do we do this? So here is one way to do it. So in this case, I remove the condition. I said I'm copying, I took what's from the else branch, I put it here. And then outside of the loop, I'm setting b of I to 0. Another way to do it is like the loop goes j from 0 to I, and then it copies. And then I have b of I equals 0. And then another loop that goes from I plus 1 to n, which again copies the same as the previous one. So this is the two ways. So you split the loop, you move the things a little bit around, and you get rid of the conditions. Okay? And finally, simplifying the loop body. So if you have loop body, if and else part, but they have like common stuff in them, you move that common stuff outside of the loop. So this is not like the best example here, but let's say, okay, never mind. So I have a of I plus a of I, and the second case I have a of I times a of I. So this I have addition, and I have a multiplication as an operation. Now, what is the addition? Addition is just multiplied by number 2, okay? And one of the ways to do it is if a of I is greater than 0, I load 2 to C, otherwise I load a of I. And then I multiply it by C. So originally I have addition and a multiplication, and I have multiplication and the conditionals. It's called
C move.
Yeah, C move, conditional move, or something like that. Yes. Yes. Okay. So you move. This applies not only to autovectorization; it also applies to regular coding. You move everything's common to the branches outside of the branches. Yes.
Is this really faster? I'd expect this to be perfectly vectorized and then to be about the same as the right thing.
This particular code is not maybe that faster. Maybe it's even the same, but it's a good example to illustrate the technique. Okay? Because I cannot put like 1,000 rows of codes on the slide. Next thing is our loops with low trip count. So the loops with low trip count, you see here the inner loop, it just has 3 iterations. And the compiler just cannot vectorize it because there is not enough iterations. Although because of the outer loop, it can get executed many times, but the inner loop is the problem. So one of the way to fix it is called loop collapsing. So you have outer and inner loops, and then you collapse them into one loop. So you see here a times 3 plus j, and then I have ij goes from 0 to 3 times n. And this loop is perfectly vectorizable, nothing fancy about this loop. Now, the bad thing about this loop collapsing is many times it's not possible. And actually, when it comes to loops with low trip count, you would probably, if you want to vectorize such loops, you would need to use some kind of manual vectorization. Not always, but yeah.
I'm surprised
Yes?
compiler's loop unrolling doesn't get this one most of the time.
This, I would expect that this loop, the inner loop, the compiler would completely unroll it, and then it will just vectorize the outer loop. That would probably happen. Yes?
How often do you encounter that the inner loop has low trip count, but it's not free, it's k, and then that k just is small?
Yeah, I had it with Gaussian smoothing, this one.
Okay,
So this is a Gaussian smoothing kernel, and this kernel size was like 5 or 3 or 11, something like that. And it's not like the power of 2, so it doesn't fit the vector length. And treating loop with low trip count here, actually we did with loop interchange. So we exchanged this loop, and then we got this code. And this code had like a big trip count. And we didn't introduce any bad memory access patterns with this, and it worked fine. Okay, somebody wanted to ask something? Yes?
In the previous example,
Yes?
can a mem set work?
Can a map check?
No.
Yeah.
Can a mem set work over here?
Yes, this is a memset.
Okay, so
So smart compilers actually convert this to memset. Probably Clang does it. Like, oh, I figured out this is a memset, just put that. Yeah. Okay. Questions? How much time do we have? 16 minutes, okay. The next problems are loop carry dependencies. So I already mentioned, loop carry dependencies is a generally problem for any kind of parallelization, GPU running, whatever you try to do, this will be a problem. Because loop carry dependencies they need to be executed sequential, like from beginning to the end. So this copy if greater algorithm, if you remember, we had this dependency on J from the previous iteration. So it doesn't vectorize well. But this guy will tell you otherwise. Yeah.
If you watched my talk from yesterday, we vectorized that.
Yeah, it is possible to vectorize, but not with compiler automatic vectorization, but with some kind of
if you use if, there is a copy if, and you can vectorize
Yes,
it.
yes. Yeah, also this prefix sum, it's not vectorizable, not in an easy way. Yes?
If you use if, that's vectorized.
Okay. If is solution for everything. Yeah. Okay. So with loop carry dependencies, there are like tricks, or there are like frameworks that can vectorize some stuff, but not all of them. And you need to there are often tricks. So it doesn't work all the time. I don't know. There is not a general way to do it. But the nice thing about vectorization, it does go from the beginning to end. So it can vectorize. You can vectorize more stuff that you can parallelize. Okay. One thing that you can do, you can remove vectorization inhibitors. So let's see. Look at this code here. So I have this complex calculation, and if I have this loop carried dependency over J. So this total loop cannot be vectorized. But then I can split the loop into two loops with loop fission. The first loop is perfectly vectorizable, and the second loop is not vectorizable, but we don't care because yeah, we hope that this vectorization of this loop, because the complex calculation, because it will make the difference. Yeah, so you can do this for any kind of vectorization problem. Like in this case, I'm removing this inefficient memory access to a vectorizable loop. I introduce this temporary B index array here. I do this complex calculation, and then I have this non-vectorizable part where I'm just copying it with this code here. So you can remove all kind of stuff, splitting loop for a vectorizable and non-vectorizable part. But the problem with this approach is just lowers a bit its performance. Instead, when you have like just one vectorized loop compared to when you have two loops. Yeah. And also the final thing is this compiler's idiosyncrasies. So it can tell you like loop not vectorizable. I cannot identify array bounds. So loop not vectorizable. I cannot prove that it is safe to reorder floating point operations. So these compiler idiosyncrasies, these are there because C++ standard requires that the compiler behaves in a certain way. You need to produce correct results. And that's why they're here. Yes?
Does fastmath encourage vectorization in that second case?
Yeah, we'll get to that. Okay. So one of the problems is pointer aliasing, and compilers can omit vectorization because of pointer aliasing. Pointer aliasing happens when you have pointers that point to the same. You have two pointers, let's say A and B, but they point to the same memory. One memory location is accessible through two different pointers, a same memory location. They can overlap partial or completely, doesn't matter. And when this is the case, then the compiler gives you like this, cannot identify array bounds or something like that. And look at this loop here. So I have a loop which has 6 pointers, but now if I call it like this, test of A plus 1, A minus 1, B plus 1, B minus 1, the compiler needs to ensure that the loop behaves correctly even when you are calling with these parameters. And in this case, it can omit automatic compiler vectorization. So if you're sure that there is no pointer aliasing, you can use the restrict keyword. So instead of int star a, you will have int restrict star a, int restrict star b, and so on. Okay, and the final is this that you mentioned. So the floating point. So look at this loop here. Sum plus equals a of phi. So if you have floating point operations, and you are like accumulating them, the order of accumulation is important. And vectorization changes the order of the accumulation, and it can produce slightly different results. Now, when you're compiling with normal standard compilation flags like O3, the compiler won't vectorize this stuff. What you can do is either pass this f associative math or f fast math to compiler, and then it will vectorize it, but you will get a bit different results. Or you can just vectorize one single loop with the compiler pragma, like pragma clang loop vectorize enable or pragma MP SIMD. Yes?
When I tried loop to vectorize enable, didn't work. What worked is pragma associative floating point on addition.
Pragma associative, I didn't know.
There's a pragma that says this specific addition is associative.
I didn't know that. Okay. Okay. Yeah, so this topic closes the topic of compiler automatic vectorization, and the next step will be manual vectorization. So some loops simply compiler cannot vectorize them. It can, especially if you have this inhibitors like loop carry dependencies, too many ifs, and so on. The compiler does not vectorize them. While and do-while loops are also possible to vectorize, but not with with automatic compiler vectorization. std has a lot of stuff that's vectorized. Did you vectorize it manually?
So I don't have anything against it. There's a library.
It's not, I thought std is part of the standard.
There is a standard CMD merged. It has no algorithms.
Ah, okay.
There is a standard parent-seq that has algorithms that are not very good most of the time. And there's extra libraries that's just on GitHub.
Okay. Yeah, so manual vectorization is using compiler intrinsics. You can vectorize that kind of stuff. I actually do offer course with AVX and Eon for manual vectorization, so I'm pitching a bit, but you will forgive me. Okay, so the thing is here, let's do an exercise together. So we have this loop called stripe color, and it's, imagine you have an image and you're coloring it like, but vertically, like in stripes, red, yellow, red, white, and so on. So you want to color it. The question is, what's the problem here? First one is the memory access pattern. Let's do what is the memory access pattern for this one? Strided. And can we fix it? Loop interchange, yes. Yeah. But let's do it like this. So this is my code. And let's do it like this. Let's do it first. Let's measure the runtime of this loop, and then let's do a pragma. And first do a parallelized version, okay? I'll do this pragma OMP parallel for, what are the shared here?
An image.
And image.
I guess color odd and color even.
Yeah, color odd.
M.
Color even. Okay. Yeah, and let's run them. So.
Should M be there as well?
N.
There is no M.
Sorry.
Yeah. Let's put default none. Okay, and see what happens. Now the thing is here that OpenMP doesn't work in my environment on Clang, so I'm going to use a GCC. This is like it just complains about the oh, sorry. So this is running it on with 4 threads, and let's see the runtime. So the image is, I don't know, it's maybe 1,000 times 1,000. I'm repeating these things over and over. So the scalar version takes 5.15, and the vector 4.94. It's something's wrong here. Let me see. What? No, sorry, something happened. Oh God. Is OpenMP enabled here? Oh God. It doesn't matter. So when I was running this experiment earlier, it was like about 4 times faster, but going from 5.15 to like 1.5, something like that. I don't know what's wrong here. It would
Perils of live demos.
Sorry?
The perils of live demos. We've all been there.
I don't know what happened. But let's try something else.
Variable?
Sorry?
Did you set the environment variable that you were talking about?
No, they don't need the environment variables. But let's do the interchange, okay? Just for you to see this, to see the difference. So how would I do the loop interchange here? I cannot do that because of this
Pull the
statement.
loop up 2.
Sorry?
Just take the loop and move it up 2 lines.
Okay. So put inside.
Yeah.
And then
switch them.
Yeah. Yeah, I know what happened. It's called, I renamed those files. This is an old version. So the original is 4.95, and this one is 1.69. So the parallelized version. And let's do the interchange, okay? So this loop goes inside. Wow. Now, what do you expect here?
I think it's going to be slower because you're doing the color thing inside the loop now.
You don't have faith, Thomas. Okay, so it went from 495 to 0.37. Yeah. So this is the size of this image. It's 3,840 times 3,840. So that's the size. So it's a really big image. But this shows you how much the memory access pattern has the influence on performance. Okay? Yes?
One thing to point out there, you use in64 for indexes inside the loop. You do i%2 = 0. I don't know if it actually stays there or if it manages to make it away. But if in64 stays there, you substantially reduced how much vectorization you get, because in64 is much bigger than what you actually need.
But this is the size.
But you do color even when you do compute the color. So you do i%2.
But this one just becomes like this one just I mod 2. It's not like a module. It's just like.
No, I mean.
Okay, I understand.
Type of I is in64.
Yeah. If I were in 32, it might be better because I have the same sizes of. It doesn't matter. Okay. And let's do the second thing. It's let's remove the condition. So this condition, what kind of condition is this one? It's
index-based.
So it's iterator dependent. It depends on an iterator. It's how it will develop. Iteration 0, it will color even. Iteration 1, color odd. Iteration 2, color even. Iteration 3, color odd. So I can change it here. And instead of this, I can put here color odd, color even. And I can put, okay, and there should be one more line, the remaining, in case the size of the image, it's not like it's an odd number, but we don't need it here. So let's see what happens now. What do you think will happen?
Probably half the cost.
Let's see. So it went from. What happened? Why I removed this thing? So it was here 0.30 something, and now it's 0.09. I copied it by accidentally here, so it's empty now. But what you're saying is like a 3-time improvement because you removed the condition. Okay, and then we can use the parallelization on this code, and it's going, instead of going from 5 to 1.5, you go for like the parallelization doesn't help a lot here.
At this point, can't you remove the nested loops and just
No.
flatten it in one loop?
No, because you're like at the end of the image, you have like a different behavior. It might be possible, but only if you would need like have separate loops for odd size of the image, odd width and even width. And let's parallelize it. So it's the same pragmas as here one. So with 4 threads, it went from 0.09 to 0.08. And what happened is, what I assume is this is now completely memory. There are no computations here. This is just a memory copy. You're copying like data from one place to another. And in that case, with very efficient loop, then parallelization doesn't help that much. Although in the first example, like here, it was important, like going from 496 to 1.47. Okay. Any questions? No? Well, we are 12:30. Thank you very much for coming. And have a good time.